Yeah, thanks. Yeah, welcome to my talk. I'm going to talk a little bit about the state of Hyper. What I mean by that is just going to talk a little bit about the status of the technical ecosystem, where we are and stuff like that. Where we're going. I got a very generous time slot, so I'll see how much of the time I fill out. I'm actually not sure, but don't want to take up too much time. But yeah, so that COF 2020 is awesome. Excited that we have a conference for the first time. We haven't really tried that before. Interesting that it has to be virtual. That's always interesting, but you know, we're virtual anyway, and it's a nice way to get a lot of people together. So very happy about that. I can't get the Discord to run on my computer, so if you have a question during the talk, please just like chime in. I'll do a question time at the end, but if there's something very pressing, feel free to jump in. I'll give one last shot. I see I can't get this link to work on the other computer. 1 second. No, it doesn't work. Never mind. So yeah, I'm mafintosh. If you don't know me, I've been involved in the DAT space in the last since the beginning, basically, for the many iterations of the project until today. I have a long background in peer-to-peer systems, doing a lot of work with BitTorrent in the past and a lot of node stuff. And today I'm basically the Hypercore Protocol lead. So technical lead, so I work mainly on all the Hypercore Protocol tech, all the primitives together with Andrew and Paul and some other people, more or less full time, working on where we're going, where we're coming from, and stuff like that, and always trying to make it better. But only like primarily the core primitives of the stack. We'll talk a little bit about that as we go along. Today, I'm going to talk a little bit about where we were as the core tech, where we are right now, and where we're going. It's a little bit of a journey, mostly on a technical point of view. There's going to be other talks. Paul is going to talk later about some of the organizational changes we made recently. So I'm just going to start out with the technical parts of it, more or less. Yeah. Drink. All right, so if you've been in the space in the DAT space for a while, you've known that we have had our stack has been plastered all over GitHub and all kinds of places. So we had that grew out from originally from a bunch of different people's projects and primitives, and it's been a lot of different things, and we never really had any consolidation on where the projects were, except we had a repo for the CLI. So there's been a lot of core tech on my GitHub and other people's GitHub and stuff like that. So recently we, as a push with the organizational changes, we reconsolidated everything into a single GitHub organization now for all the core tech. That GitHub organization is called Hypercore Protocol. So if you're interested in following along in the core development of the peer-to-peer primitives, check out that GitHub org. It has everything that I like to call blessed, which means that it's everything we support really heavily. If you open issues there, you'll get an answer, stuff like that. We've spent a lot of time on that. In addition to that GitHub org, we have another GitHub org for the networking stack called Hyperswarm. But it's the network stack using Hypercore Protocol. That's just a GitHub organization we all had from the beginning, so we didn't want to merge too many things at once. But yeah, so that's where the action is happening. Go in and follow the repos if you want to. So I'll just give a. I think most people here probably at least know about some of this stuff from before, but I'll just give an extremely brief overview of like what it is in the core Hyper community, Hypercore Protocol community we work on. So we primarily work on this thing called Hypercore. So Hypercore is our primary data structure. it's what we call an append-only lock. People in the community has probably heard me say append-only lock 1,000 times, but it's our main data structure. So it's where other projects work on graphs or Merkle graphs or other kinds of core data structures. Our core data structure at the end of the day is an append-only lock. So it's what we build everything on top of, and that's our main thing that works in a peer-to-peer environment that distributes, that has all the security and all this stuff. It's our main thing. Then the other thing we work on in the core team is this thing called Hyperdrive, which it's a thing that builds on top of Hypercore that projects a file system. So it's basically a file system that works by just storing stuff in hypercores. So if you know more about the history of that, basically in the beginning of that was kind of like a Git system where you can put all kinds of data in. Then slowly it evolved into a file system, and that's where some of the first versions of Hyperdrive was used to build a shareable file system. It's gone through many changes since then, and now it's in this separate, well, it's always been separate, but it's in this formation today where we have all these new features like mounts for collaboration and stuff like that, but I'm sure other people will talk more about it. But basically, that's our main file system data structure, and we heavily support that one. And I'll give a little demo of that later on, show you how you can use it through the APIs. Super cool stuff. Then this one, core stores, is another core abstraction we work on. So I actually don't know, that's not something I have talked about a lot in the past. It's one of the new additions to the stack. So basically, core store is an abstraction for using many hypercores at once in an easy way. So when you work on data structures on top of hypercores, you often have an environment where you need more than one hypercore. For example, Hyperdrive, the file system, uses many hypercores. It uses a hypercore to store your metadata, the file metadata, the file names, the modes of the file system, modified times, all these kind of things, and an index to find files quickly. And then it uses another hypercore to store the contents of the file. In addition of that, if you mount another Hyperdrive inside Hyperdrive, if I mount one of my friends' Hyperdrive, that also needs hypercores to store data. So core store is just a simple abstraction for not having to manage that yourself, but basically get something that manages all that for you. Very nice, very simple. We'll talk about that later on in the demo also, but that's also part of the core stack. And then finally, the final core primitive we have is something called Hyperswarm. Hyperswarm is our peer-to-peer connection stack. So it's the networking layer that makes everything talk together. So all our data structures, it's peer-to-peer, so they need peers to talk to. So our Hyperswarm is our abstraction that has like a discovery network, a DHT for finding peers, ways of finding peers locally. It does all these interesting things to make sure that connections work, like UDP hole punching, stuff like that, connection management. So it's our like grab bag of peer-to-peer things in here. But if you're interested in that part, that's the only thing that's not in the Hypercore Protocol org. So if it's more than that, check out the Hyperswarm GitHub repo, GitHub organization. Cool. And then this one it's an addition. This is like a little helper Andrew has built. Andrew, who's also part of the core team, who's also going to talk later. The core store networker. So basically, Hyperswarm, everything we build in the core team, all the core abstractions are very independent and somewhat low level, in the sense that they're very modular and don't necessarily depend on each other. They can be used in all kinds of ways. So, like an example of that is that Hyperdrive doesn't have any networking baked in that comes from the outside. So that means that you can also work with the abstractions to make it work on other networks outside of Hyperswarm. That's not always, if you have to handle all that code, that's not super trivial. So Andrew wrote this really nice thing called the Core Store Networker. It used to be called Core Store and Networking, but we consolidated it into this nice little module pretty recently that allows you to very easily take a bunch of hypercores and distribute them on a network efficiently without having to spin up a swarm for every hypercore, and manage like all the things involved with putting hypercores in the network. So it's basically just like taking the hyperswarm, taking core store, treating all that plumbing, getting it to work with a simple little one-liner interface, and I'll show more about that later. But it's really cool, and it's highly recommend that if you're using data structures to use more than one hypercore, which probably most things do. So again, this is mostly just aimed at people who work on the ecosystem. So just want to go through these from a high level and just talk about the stability and a little bit about what we're working on. By stability here, I mean mostly, does it crash? Luckily, all the things in the core right now are pretty good at not crashing too often, at least like non-catastrophic errors. It's been pretty stable recently, but more importantly than that, things like API stability. So that means if you're building stuff on top, what's the chances of the APIs changing in a way where you would have to deal with that, which is not fun. So the first one, Hypercore, our main thing, super old and super steady, and it's been stable for a long time. We basically consider the API there frozen and I mean that in a positive way of like it's not changing. If you're building something on top of this one, no problem. It's probably going to work. We sometimes in the past pushed up breaking changes for the protocol. We recently did that when we really worked at home without you having to go in and configure networks and firewalls and stuff like that. That's also been we've been following along the scale of this as we pushed out a big push here in May. It's been working really well so far. We're really happy. Networking can obviously always be better, but there hasn't been any big problems showing up. We did some tweaks here and there to try to make the ergonomics a little bit better and try to make a little bit easier to make it faster to do discovery and stuff like that. We're still doing some tweaks on that, but overall it's actually been really good. We do some very interesting heuristics here now also, where basically everybody who runs like in most of these P2P networks, everybody who runs a Daemon client or is using the swarm also participates in growing the swarm, i.e. like storing info for helping people route on the DST and stuff like that. We do a bunch of heuristics to make sure you only do that if you're on what we consider a good network. That means that you've been online for a while, you have a router that's hole punchable in the sense that they can help serve these hole punches to help people connect to other people and stuff like that. And that's done really good work for keeping our network healthy. So every node in the DST is reachable normally and stuff like that. That's been a big problem in the past when we worked on this in the past. So very happy with this layer. It's super stable. Also, if you're building stuff outside the ecosystem, the swarm, like I said, it's super modular, so it doesn't bake in stuff, and you can use it with all kinds of things yourself. It's just a bunch of connections. Maybe we can talk a little bit about that as we go along. Cool. Core store. Yeah, it's some very compressible slides on it here, because this one is also pretty stable and frozen. So core store is, like I said, the abstraction for working with many hypercores. It's been working again super well. A few bugs. We keep changing the internals here a little bit, but like again, the overall API is pretty stable and frozen. I don't think we'll do anything big with that, but the internals might change. So don't rely too much on those if you don't want to break. We recently broke some internals there that broke some ecosystem stuff. That was unfortunate, but it happens sometimes. But the overall API is pretty good. And then finally, Hyperdrive. So Hyperdrive is still only marked as stable because we have a bunch of stuff we want to do here, and we keep doing to make it scale better, to make it faster, to make it more usable of all kinds of things. So APIs might change here, but we don't change anything here that's at least not in a very strong way backwards compatible. Like I said, we did a big push recently and got a bunch of new users on the network, and obviously we don't want to break anybody. But we have a bunch of stuff we want to do with this one. So yeah, if you're building lots of stuff with that, I will encourage you to come join the discussions on Discord and in the repos, so we can stay up to date on that. Yeah, that was just a quick overview of the core tech. So basically, throughout the history of Hypercore and Hyperdrive and this whole my involvement in the community and also just that, we always had a massive focus on heavy modularity. So like tons of modules. The stack is it's node based, so it's a bunch of npm modules. Bunch of things that like follow pretty strict Unix philosophy in the sense that do one thing. It's been really great because that's been really good for engineering. Heavy modularity, though, also have a pretty big downside in the sense that it tends to create, the main feature is also its main disadvantage is creates module hell. So what do I mean by that? I mean that it used to be when you build stuff with that and Hyperdrive that you would have to require 20 modules first, and you kind of figure out how to work together, and then you get going with this very highly modular stack with a little buy-in. But like getting to that point was pretty hard if you weren't involved in the community pretty heavily. So we did a pretty big push recently to try to make this onboarding thing easier, spearheaded mainly by Andrew, who's again going to talk more about this later. But we basically introduced a daemon service that did all this requiring the modules, so you didn't have to manage your swarms yourself. Also meant that we could have a swarm long running on a computer, which is way better for swarm health and the network health to make it sure it keeps running. It meant that people who wanted to interact with hyperdrives didn't have to roll a bunch of modules, but they could just connect to this daemon and get a bunch of APIs. So it was really good. It was a really good push. It basically tried to make the best of both worlds, where we still have the modularity. If you want to hand roll a bunch of stuff, you want to use all the modules, you can do that. But if you want to get this like batteries included experience, you can get that with the daemon, where you just install it and run it, and you use the stuff. You don't have to worry too much about the tech. So the very high level, the daemon architecture looked kind of like this, where internally we had a bunch of hypercores, basically a core store, and the network layer, and set that up in a way that scalable, make sure that it always worked, and did all these heuristics I talked about with only connecting to the network when you were sure you're in a good place. The daemon then used that to make a bunch of hyperdrives that you could access through this RPC layer. The RPC layer we used was this protobuf-based RPC layer called gRPC, which is pretty heavily described on the internet. And then the daemon also, in addition to a HL service where you could run things as a fused file system, so access them through the file system in addition to the RPC. Yeah, the daemon, it's been, like I said, been working really great. But it was only for hyperdrives. So we pretty recently wanted to do a push to get hypercores exposed through the daemon. So you can start building more things that are not necessarily file system related. Lots of things in the ecosystem run on Hypercores. First of all, we have a bunch of data structures we built. There's the Hypertry, which is our little key value database. We have a bunch of streaming modules that all uses Hypercores, and then a bunch of others. Hyperbatch is one I recently wrote for just managing a bunch of big blocks in Hypercore. Point being, we have a ton of ecosystem data structures out there that we would love to be able to use with the Daemon, and those are not relying on Hyperdrives, they're relying on Hypercores, like the underlying feeds. So pretty big motivation to getting Hypercores to work in the Daemon. And then also there's a bunch of ecosystem projects out there, also from people here that's doing talks at the conference that is also using a bunch of Hypercore stuff in addition to Hyperdrive stuff. So it would be great if we had a Daemon system that could help with all those things. So we sat down and we're like looking at engineering. We're like, we can expose a Hypercore on top of this, but it felt a little bit complex once we started doing it because we basically already had this Hyperdrive on top of a Hypercore, so then we're going to have a Hypercore on top of a Hypercore. It was like, it felt a little bit weird. So at some point we were like, we need to look at this again. So Andrew did this big push to just flip the Daemon upside down a little bit and turn it into this experiment called Hyperspace. Don't know if anybody has seen it on GitHub yet. We have put up a little sneaky repo so we could experiment with it in public. But it's going to be the next Daemon version we're releasing. So the successor to the Hyperdrive Daemon. And it's super exciting. So the architecture is basically just flipped around a little bit. So it's just Hypercore networking. Both of those are exposed over an RPC layer. And so much simplified. We kind of made this, and then we've been very excited about how good it works, and it's definitely it's going to be really good once we get it out. So we changed from gRPC to this little new thing we made called HRPC, just because the RPC layer in this is much more simple. Like in the Hyperdrive Daemon, the RPC layer had to deal with a bunch of stuff like streaming files, and all these kinds of complex RPC operations, like a bunch of streams. Whereas in a Daemon that just exposes Hypercores, because the Hypercore API by itself is very small, the RPC layer can be much simpler because it's just has to expose the Hypercore operations, which is just simple gets and puts and stuff like that. So it allowed us to switch out the RPC with something that's much smaller and much simpler, which we're always looking to simplify things. So it's very exciting. And I think Frando actually got it working already, the RPC layer and Rust. So that was a good signal for us that these things are simple enough that you can reuse them in other environments. So what's cool about the Hyperspace Daemon? Well, it's really cool because it has a one-to-one mapping, the remote API, the API used to interact with the remote Hypercores, to the normal Hypercore API, which means that anything built to use Hypercores or core sorters just work with the Daemon. You basically don't have to change anything unless you're doing some inspecting some private stuff and stuff like that. So it's really, really exciting for us that way. So if you ever used hyperdrives and you use them in what I call raw mode, like outside Daemon, then it kind of looked like this before. Sorry, it looks like this today, where you require a module, and you would make a hyperdrive, and as the storage parameter, you can pass in either a file system path, then it just internally creates a core store on that path, or you can pass in a core store, where it should make its internal hypercores it needs from. So if you were to use this today, or sorry, in the future with the Hyperspace Daemon, only a little bit more complex. The only thing you need to do is you need to make a client to the Hyperspace. That gives you a core store, and then you use that core store instead. And then it all works. So the hyperdrive itself doesn't know that it's running remotely. It thinks it's running locally because the API is the same. So it's super exciting. We did a bunch of tests just to see if there was something we missed, and we actually got all our internal data structures working pretty easily with the APIs. I'm sure there's, I know there is areas where we still need some tweaks, but it's just yeah, it's been working really well. So we're very, very excited about that one. So the idea is that the Hyperspace daemon will replace the Hyperdrive daemon. We struggle a little bit with the name because we realized by calling Daemon the Hyperdrive daemon, we kind of boxed us in. So moving the Hyperdrive to be userland was a little bit that made the name a little bit silly. So we landed on the Hyperspace because we thought it was a really good way of encapsulating everything. So this is going to replace the Hyperdrive daemon internally. But we're going to have the same functionality we have today, because just instead of all data structures running inside the daemon, then now they're going to run outside in what we call userland. So you're going to, the Hyperdrive is going to run in your program, not inside the daemon. But it works better that way. And yeah, like I said, anything that uses Hypercore can theoretically run on the daemon. So if you're building some app and you don't want to worry about networking, or you want to have interop with everything else in the computer, you can offload that to the daemon, or you can even embed the daemon in your app if you want other people to be able to use your stuff. So it's super powerful. Very excited to ship that at some point. Then we still want to have all the Hyperdrive functionality exposed as a service, stuff like the fuse file system and stuff like that. So for now, we moved this for Hyperspace into a little service called Hyperspace Hyperdrive that has all the CLI for the Hyperdrive and everything. So it gives you the same functionality you get today with the daemon. If we bundle that into one thing at some point, I don't know, we'll see. But right now, it's put out here in a very nice and modular way. Yeah, like I said, we're very conscious about backwards compat, not breaking anything. So the new daemon will do auto migration of existing data, which means that hopefully you won't notice when we flip to the new one, unless you're using the remote API of the old one. Then there's a module for that also for getting the same API with the new daemon that Andrew made. So yeah, really cool stuff. Very exciting. This is super experimental. It's in a pretty good state right now. The new daemon, we basically switched to bug fix only mode a week ago, and we're just like making sure it's programmatically stable before we push it out. But you can install it today if you want to, but like at your own risk. But it's super exciting, and I'm extremely excited about it. I've been using it for a lot of stuff. It's been really fun to work with, and it's super fast also. And yeah, it's just I don't have anything bad to say about it. It's very exciting future. Yeah, cool. That's the end of my slide. So I thought I would just give a little demo for the last time and for the last of my time. And yeah, I'll just quickly check the channels and see if there's anything. Whoa. I don't know what I'm doing. Oh, there, it's up there. Cool. If you have any questions about anything core related, start thinking about them. Maybe we'll have some time after. Otherwise, I'm in the Discord, and I'll be around also, so we can talk about anything. So the first thing you want to do, if you want to try it out, is you want to install Hyperspace from NPM. You just do it like that, normal way. NPM install the Hyperspace, and then when you run that, you can run the CLI. I'm running that over here, my other tab. And what it does is it exposes this Unix socket, a tempter. That's just a crazy tempter on Mac. And it's just make sure that it works still. And it still works. That's awesome. So this is a remote feed, but it has everything the normal Hypercore has. So you can do stuff like append data to it in exactly the same way as you would a normal one. Piece of data. And, here that it has 2 pieces of data, just like the normal one. It also has, all the normal all the sync properties that the normal feed has. So you can expect the length, you can expect the file, the byte length. With the normal one, you can expect the, what's the key. You can do that exactly the same way as you would a normal feed. So run that. So 4 length, byte length, and the key. It's all extremely similar API. I think we have like almost everything on the public API. You can even do stuff like inspect how many peers it has with the peers array. So if I print that one out, I'll probably get 0. Yeah, I have no peers. Right, so that's like, you don't need to do any kind of special switching between the local one and the remote one. Basically the same thing. And you can also do, just do the last thing. You can do stuff like the normal read streams and stuff like that. So you don't print anyone out. So all that stuff works. That's just my high. So this means that you can, you can take your core store and you can require stuff like hyperdrive. Do the try instead, it's more fun. Right, stuff like the try or KB store. You can do try. I think I can do this. Actually, I'll just name this one so it's easier for me to remember. My namespace. These core stores can have a name, so it's a little bit easier to manage them. Because you can just use the default one, and then you always get the same one out. Let's just print it out when it's done, and then make the database, and then see if I got the API right. Let's see if that works. I think I need to put an all here because there's no storage. There we go. So you can see here, stuff like this is the try. It doesn't know that it's running on the daemon, but it works because it has the same API. And here we got the key out. So what we can do is, we can make another program. Open that one. I can take the key from the feed I just made. Let's try, and we can just copy over the code here. And then here we can get the feed out. Star. Just get this feed out real quick. Then we can load the key out. But here, we can run another program that accesses the same feed and gets the value out. The point being that you can run many of these on the same computer. So what I can do is here I can run this one, then I can open a new tab, and I can run it again. But it's just running against the daemon. So we can all of a sudden use this in many places on the same computer. And the super cool thing is that this is not all the Hyperspace has. It also has a networker. So access the networker on there. Let's see if I got that right. It's called network. Yeah, there we go. The networker is a remote instance of the core store at core store networker. So core store networker has everything you need to expose things to the network. So basically, just has this one very important method. Well, it has a couple. It has the peers and all that stuff. Also works in the daemon, but it has this configure method where you can tell it to expose a hypercore on the network. So what we can do here is we could say network feed.ready. Let's take the time quick. Yeah. Network configure feed.discovery key. And then you can get the announced, should it go online? Should it be announced from your computer, or are you just looking for other people? Here I'm going to do both. So what this does now is that it tells it to take this feed, put it on network, host it, but also find other people. But you don't need to set any of that up. It just uses the daemon. So if you were to run this, I'm actually hosting it on the network, and when I kill my process, it stops hosting it, and there are some options you can give to keep it running. So point being, you can very easily get set up now with the ecosystem with all the data structures and all the apps built using the daemon. So you don't have to configure any of this network stuff, or manage storage and all this stuff. You can just punt off to the daemon very easily with this new API. So it's super, super exciting. So like I said, it's not fully released yet. You can try it out. Be aware that it's experimental, but we're gonna release it stable soon. Yeah, that was my last thing. See, I have 10 minutes left. I'm gonna stop the screen share. If anybody has any questions, now's the time. Oh, that was a whole chat down here. There you go. Yeah, you're welcome, Paul. So the next talk is in 10 minutes, I think. So we can either take some questions or we can take a little break, I guess. I see Paul has been answering a lot of questions also. That's okay. Scalability testing. I'm just going to comment on the chat here now. We did various forms of scalability testing. So we actually have not just yeah, I think you should roll with it, Paul. I'm gonna comment that for relay that for the stream. For scalability, we've done various forms of testing. We did some scalability, just like performance things on a single core, like how fast, what's the overhead of the hash trees and all the stuff we do to send data. And actually, that one has been really, we have almost no bottlenecks there. I have a gigabit network at home, and I can saturate that network on hypercores, which I can't even do on HTTP connections. So that's really good. Super fast stuff. For the spreading, like connecting to many ones, we did some simulations in Mininet, which is like a virtual network, and to check that the swarm works, and that we fixed a lot of bugs there. That one is pretty scalable. We do have some work to do on like making sure that connection management and stuff like that works better inside the daemon, i.e. like that we recycle connections or stuff like that. We haven't done much work with that yet, but that's me and Andrew's main focus right now. Like I said, the main bottleneck we have with just running, let's say you wanted to run a million hypercores and process, that's probably not going to work very well right now, because you're going to run out of memory if you have them all running at one time. The daemon does some caching thing where it makes sure that it only loads them when it needs them and stuff like that. So that's pretty good for that. So there's some scaling stuff to do there. you wanted to go big scale. But nothing in the protocol really that shouldn't scale. It's just engineering. Oh yeah, promises. Sorry, yeah, promises in Hypercore. I can just share my screen for 1 second. Rachel said that. It's good you brought that up. So basically, we took the chance when we were making this remote Hypercore to also add promise support to everything, and we'll upstream that at some point when we're ready to call this stable, I think. So in the Hypercore now, you can make you can await it. So you can do this. That's right. So you can do await there, and basically anything that's you can wait again also. Yeah, you can print it out. And we do some stuff now also with, like let's say you just got the promise out, then you can actually you can use that promise to cancel the operation like this. You can pass it down to the cancel function, and then that cancels the get and stuff like that. So we did a lot of work on that. That's gonna reject the promise. So this I get, and then did this. Oh, because it's too fast. My bad, because it's local. But yeah. Otherwise it would. Yeah. Stop sharing my screen there. Yeah. Let's see here. All questions. Will the Hyperspace Daemon make bundling and package for non-technical peers all set up? Yeah, totally. So Beaker actually does, or just runs it if nobody else is running it. You can do that with this API. It's 2 lines of code to run the daemon in the CLI. In your app. We are gonna at some point add, obviously that then if you're using multiple apps on your computer, then if you shut down yours, you want somebody else to run the daemon. We'll probably do some little multi-manager thing, so somebody failover it's called takes that over. But I can just go back here again real quick to my screen share just to show if you wanted to run your daemon, to show that I'm not just making it up. The only thing you would do is I would probably want to start this one first. It's that in addition to a client, this one has a server. You can remember how to run this. We have a little temporary work for this. We're going to move this into the protocol once we're happy with it. I'm just looking if it's okay. I think I can just do this. Oh, it's open. There you go. That's it. That's all you need to do. Is you just need to make a server and await open, and it's running, and then you can close it. So very, very easy. 3 minutes. Is there any other questions? And thanks for listening, and also big thanks for the organizers. I forgot to say that in the beginning. It's an unthankful job to organize these kind of things. So very, very big thank you for that. Also, if you're more interested in this stuff, Andrew's going to talk way more about it in later tonight in the Beaker talk, because Beaker is a big consumer of the daemon. So he'll probably explain it much better than I did. What's the last question here?
What's the primary use cases that you imagine will drive Hyper strategy now and over the next year?
I'll just answer this real quick. I have 1 minute, I think. Yeah. Basically, we're focusing on, at least from my point of view, making sure all the low levels work real fast and that there's no bugs and it's all fast and scalable. So we'll keep doing that and add more, making sure everything is stable. If we're in a year from now and we're still using Hyperspace, it's pretty good. Sorry to take the last time.